Okay, so today we're going to be talking about the roller coaster problem that was assigned on the College Board website. And here we've got a roller coaster going from A, B, C to D. And we know that from B to D, this is a circle, part of a circle. So question A leads off with stating the direction of the acceleration at points A and D. Okay, so for this problem, what we want to do to think about the direction of acceleration is to think about the direction of the net force, right? Because we know that the net force is equal to ma, right? The net force is a vector, and so is acceleration. So if you have the direction of the net force, then you have the direction of the acceleration. So at A, we can think about the force of gravity, which points downwards. And we've got the normal force acting on A about up and to the right, because it's perpendicular to the ramp there. Okay? All right, so if we kind of think about this by adding these two vectors, just qualitatively using the parallelogram rule, you'll find that the net force is kind of down and to the right. That's the net force at A. Now, for the acceleration at D, we're undergoing uniform circular motion here briefly at the bottom, just briefly while it's at D. And here we've got the same force of gravity pointing downwards, and the normal force is actually going to be pointed upwards. I should have drawn this better, but it's going to be longer than the force of gravity. Okay, so the direction of the net force here, since we're undergoing uniform circular motion briefly, is going to be upwards. Okay, so that means that the acceleration is up at point D. So for question B, we've got at part C, we have two forces acting on the roller coaster at part C. So here we've got the force of gravity pointing downwards. And the normal force is, again, perpendicular to the surface. So I'm just going to draw this like dotted line that's tangent to the path here. And the normal force is perpendicular to that, Fn. So for the normal force, something like up and to the right would suffice. And for the force of gravity, downward would be fine. Okay, on part C, what we are now told, we'll be using this information for C and D, is that the students analyzing the roller coaster have modeled the motion after this graph here, as well as this equation x of t. Okay, so for question C, we want to talk about the first half of the graph from 0 to 5 seconds. Okay, and we want to come up with two reasons as to why this graph or equation match the actual motion of the roller coaster. So I'm just gonna list off the two easiest ones, I believe, which are: first, check to see that what it's doing in the beginning is really what it's doing. So the roller coaster started at rest. Okay, so the best thing to do is just note that we're giving a distance graph here. So if you check the tangent line, does that look like it's horizontal? Okay, so yes, it does look horizontal, which means that the speed is equal to 0 at the beginning. Okay, now a second way, so that's the first thing, and then the second thing that you can do, or I did for my solution, which you can look at the key for, was for x of t, actually get the second derivative. Okay, so x double prime t. Okay, so when I did that and I just plugged in any of these times here from 0 to 5, so actually plug in 0 to 5, anything there, and just confirm that that's a positive number. Okay, so from calculus, you know that if the second derivative is a positive number, then the graph should be concave up. Okay, which is what we have here. So that graph does match what we have for the motion. Okay, so for D, we want to talk about the second half of the graph, 5 to 10 seconds. So the second 5 seconds. Okay, and this time it's the opposite. We want to come up with 2 reasons as to why the model falls apart for the second 5 seconds. Now, again, we're going to go with the easiest thing first, is just think about what it should be doing at the end. So at the bottom of this of the roller coaster track here, we're at D. Like, should that be? It should be where it's the fastest, right? You can even just think about it in terms of energy conservation. If it starts here at rest, you have like all the energy is stored gravitationally. Here at D, all the energy is now stored kinetically. So if anything, it should be the fastest. So what does that mean in terms of our graph? At 10 seconds, what that means is that the tangent line of this curve should be the steepest. It is not the steepest here. Actually, it's pretty close to flat here. Okay, so this is the reason why that doesn't work. On top of that, on our way to D, it should be speeding up. Okay, now our graph opens up sideways like this. Okay, that does not line up with what the graph is doing, or rather the roller coaster is doing, because it should be speeding up. So if anything, the curve, not just the endpoint, but the whole curve should be actually increasing in its curvature here to accommodate for the fact that this slope, like, let me just draw what it should be. It should be kind of like this to show that's faster. So this slope has to be the steepest here because it's the fastest at D. Okay, so there's our 2 reasons. Basically, you want to look at the end cases and what it's doing like in the middle. Okay, so the style of analyzing graphs, the best thing to do is to think about what it's doing at the ends, and then also what it's doing in the middle parts. Okay, so think about that moving forward. There are ways to check to match and make sure that what your model or your graph, you want to make sure that it matches with whatever the object is doing in actuality. Okay, so in this problem, for E, what we want to talk about is how we would get the height difference between point A and point D. So in this case, what we want to do is go with energy conservation. Just because the track is such a weird shape, the acceleration is not going to be constant at all. So that's going to be challenging to talk about this in terms of just the geometry of the track. Now, what we can do to get around this is to just talk about energy. Okay, so here we know that initially all the energy is stored gravitationally at the beginning. So this is at A for the Earth cart system. By the time it reaches point D, it's at a height of 0, if we define D as 0 height. So all of the energy on the in the system is now stored kinetically. Okay, so here what we got is we've got an expression for the EG initially, mgh, and we also got EK here, equals 1/2 mv squared. Okay, so if we wanted, we could determine the H by talking about energy conservation. Okay, so it's one point to talk about energy conservation. All right, the second point is to first think about, hey, do we have everything to even get at this H? Okay, here we've got G. That's fine. That's constant. We also have the mass of the roller coaster. The second thing we need to tackle is getting this velocity. Okay, so we can use the student's model and assuming that we now have the correct definition of x of t, what you want to just say that you have to take the derivative once with respect to time of this position function. And then what you want to do is just say, all right, let me get this velocity for 10 seconds. Okay, so whatever this is your velocity at 10 seconds, and that would go here. Okay, so identifying that you have to take the derivative is the second point of this problem, and then plugging it back into plugging 10 seconds in for that equation to get this velocity is the third point of this problem. Okay, so I'm going to explain this in a slightly different order than I did on my key. So for part F, we want to figure out the normal force. They don't flat out tell you, but they say find the force that the track exerts on the car. Okay? That's the normal force. So in other words, find Fn. All right? So there is no equation for Fn that is universal. It's always situational. So at the bottom of the track, so at point D, we know that there is a force of gravity acting on the car and a longer normal force acting on the car, pointing upwards. Okay? And this is the force that we want. Okay? So in order to get at this force, we need to do a few things here. So first thing, your first point is by dropping the net force equation for circular motion. Okay? And your second point, so that's the first point. The second point comes from the fact that you get the net force from saying the net force is equal to the difference between Fn and Fg. Okay? Remember, for circular motion, it's slightly different. So if they gave you a loop-the-loop, it's actually the opposite way. Because in circular motion, we treat it's in minus out. Okay? And what I mean by that is that you draw a force diagram and then there's a circle. You have to imagine a circle. So whatever points inwards gets the plus sign, and whatever points out of the circle gets a minus sign. We're lucky here because that worked out. Up is always positive and down is always negative. But if it was a loop-the-loop, which doesn't happen in this problem, but I just want to talk about this. If it was a loop-the-loop, Fn and Fg would point inwards, into the center of the circle. Okay, so just be careful about that. So that's the second point, is walking them through how to get the Fn. Okay, so the last 2 points for this problem come from the geometry of this. So first off, yes, we can get the Fg, and we can get the normal force if we have this value here. And we have the mass of the roller coaster, okay? But we also need the velocity, which we can get from the derivative for 10 seconds, okay? And the last 2 points for this problem come from talking about the radius. So here, the circumference is 2 pi r. Okay? And from B to D, 4 times of the distance from B to D is the circumference. Okay? So what you want to do is you want to just make sure that the r you use is in fact obtained from this relationship. Okay, so we know that this, from the problem, we know that this is 100 meters going from B to D. That's mentioned in the previous parts. So that's one point, is to acknowledge that you have to talk about radius and circumference. And then the final point of this problem is to just state that, yes, this is really a quarter circle that we have. So it's 4 times this quarter circle is equal to the full circumference. Okay, so when it comes to getting this radius that we're going to be talking about, it's 400 divided by 2 pi. So that's what goes into this r here. All right, so that's AP Classroom FRQ1. Hopefully this helped on top of my key. Let me know if you have any questions, and good luck.